All right, let's talk about something huge. We're going to use math to tackle one of life's biggest questions. This is all about survival models, the science of predicting a lifetime. So yeah, let's just dive right in.
I mean, it's a question everyone's asked themselves at some point, right? It feels so personal, almost unknowable, maybe even a little bit scary. But for a whole branch of math and statistics, this isn't some big philosophical mystery. Nope, it's just a variable, something to be solved.
And yeah, while that question feels so personal to us, the answer, when you zoom out and look at the massive scale, is actually the bedrock for systems we all depend on. We're talking everything from healthcare to finance.
And believe me, the applications are just incredibly broad. This is not just some dusty academic exercise. I mean, governments are relying on these models for public health policy. Insurance companies, they're using them to figure out your premiums. And pension funds absolutely depend on them to make sure they can support people through retirement.
Okay, so how on earth do you even begin to model something as wild and uncertain as a human life? Well, the first step, and this is absolutely crucial, is to take a bit of a conceptual leap. You have to start treating a person's future lifetime as a random variable.
So let's start at the very beginning, with a newborn. Actuaries define a variable, they just call it T, and it represents the future lifetime of that baby. It's random, because, well, obviously we don't know the outcome ahead of time. And it's continuous because a person could live for any exact amount of time, right? Like 82.47 years, for example.
Now, to describe this t variable, we use two key functions that are basically just mirror images of each other. You've got the distribution function, which is the probability of dying before a certain age, and then you have the survival function, which is the probability of surviving at least to that age. See, they're really just two sides of the same coin. If there's, say, a 10% chance of not making it to age t, then it stands to reason there's a 90% chance you will.
Okay, that's all well and good for a newborn. But of course, most of the time, we're not talking about newborns. We're usually interested in the future lifetime of someone who's, already made it a certain number of years.
And as you'd expect, actuaries have a very specific shorthand for this. Let's take a look at this one, 60_Q40. It looks a little weird, but it's simple. The 40 at the bottom, that's your current age. The 60 up top is the time period we're looking at in years. And the Q stands for the probability of, dying. So this whole thing just means, what's the probability that a 40-year-old dies within the next 60 years? Or, put another way, before they turn 100.
And a really core idea here is something called the consistency condition, which honestly is just common sense wrapped up in math. It just says that to survive a long time, you have to survive all the short times that come first. It makes perfect sense, right? So the chance of a 30-year-old living for another 20 years is just the chance they survive the first 10 years, multiplied by the chance that now as a 40-year-old, they survive the next 10 years.
Okay, so far we've been talking about probabilities over big chunks of time, like years. But what if we want to get more granular? What if we want to know the risk of death not over the next year, but in the next second? For that, we're going to need a much more powerful, more precise concept, and it's called the force of mortality.
This is represented by the Greek letter mu with a little x next to it, and I want you to think of it like a speedometer for your mortality risk. While the probability of dying over a whole year might be, say, 1%, the force of mortality tells you the underlying risk at this exact moment in time for a person of age X.
Basically, what it means is that the probability of dying in a super short period of time, like a day, an hour, or even a second, is just that tiny slice of time multiplied by this underlying force of mortality. It's the raw, instantaneous risk factor for that exact age.
Now, to make this less abstract, let's try a little thought experiment. Imagine you gather a massive group of people, and they are all turning exactly 50 years old today. Now, you watch them for just 1 hour, and you count how many pass away. If you take that very small number and then scale it up to an annual rate, multiply by 24 hours times 365 days, what you get is an amazing real-world estimate for the force of mortality at age 50, mu 50. It's the annualized rate of death based on what's happening right now.
All right, so we have our building blocks, right? We have the survival function, and now we have this powerful idea, the force of mortality. Now we can finally put them to work and calculate the one number that everybody really wants to know, life expectancy.
But first, a quick but important distinction. There are two ways to measure this. There's curtate expectation, which just counts the number of full birthdays you're expected to have. But then there's complete expectation, which is the more precise one we usually talk about, and it includes fractions of a year. And because people pass away all throughout the year, not just on their birthdays, the complete value is usually about half a year longer.
So let's look at some actual numbers from the English life tables. For a newborn male in the UK, the complete life expectancy is 73.413 years. That's the average age of death for that entire group of newborns.
Okay, now check this out. A 21-year-old is expected to live another 53 and a half years. But wait, do the math. Their total expected age is now 74 and a half. That's a full year longer than the newborn. So why? Well, it's because they've already survived the high-risk periods of infancy and childhood, risks that are still baked into the average for the newborn.
And this same logic holds true your entire life. A 70-year-old is expected to live for about another 11.2 years, bringing them to an age of around 81.2. You see, every year you survive is kind of like a small victory against the odds, and it pushes your own total expected lifespan just a little bit higher.
So, look, these calculations are fascinating for us as individuals, for sure, but they go so much farther than that. They actually form one of the most powerful metrics we have for understanding the entire state of our world.
And this really tells the global story. Just look at this data from 2015. The range is just incredible. Life expectancy at birth in a place like Monaco is way up in the high 80s, but in Chad it was under 50. I mean, think about that. That's a staggering difference of almost 40 years.
And that's why this one single number acts as a powerful global yardstick. It reflects everything, from basic sanitation and nutrition all the way to access to super advanced medical care. It tells us in really stark terms about the overall health and prosperity of an entire nation. Which, it kind of brings us to a really fascinating final thought. All of these models, everything we've talked about, are built on historical data. They're built on the patterns of the past. But what happens when the future stops looking like the past? With all the breakthroughs we're seeing, gene editing, AI diagnostics, personalized medicine, we are literally pushing the boundaries of human life itself. So the question is, how do you model a future that might not play by the old rules? And that, right there, is the next great challenge for this entire field.